Hello everyone, my name is Sai Harshita. I'm working in speech processing lab under Dr. Chiranjeevi Yara. My project title is Syllable Stress Detection, which I've worked for the past 2 months. So let us first see my objective. Now, what my main motive was to create different models based on like DNN or VA-DNN, contrastive learning, etc., in order to detect the cerebral stress. Now, why I'm doing this is for the prosody analysis. Now, what is prosody analysis is? Now, when we say a sentence, not only the words but also the pitch, volume, etc. Like such terms also matter for any model. Now whatever models are there for us, like currently like Alexa or Siri, they do not talk more like humans. So, in order to make them more humanly soundable, we are trying to work on the basic of it. So if we are able to detect stress on the syllables, we all know what syllables are, right? So in a word like really, it's like really or really. So the first word has the stress on the second syllable, that is li, and the second word has this, stress on the first syllable, that is re. So basing on that particular stress, we can try to identify the emotion. So prosody analysis is nothing but analyzing the inner meaning of any particular sentence if we give a speech. So in speech to speech models, if we add this prosody analysis, the model might perform better. That's what we are expecting. That might be our final target or something else. But right now, what I did was syllable stress detection, and I did that on German and Italian datasets. Like we'll have native English speakers, and also we speak English differently. In a similar way, German and Italian people also speak English differently. We have worked on those datasets and developed different models. So I've gone through automatic detection of syllable stress using sonority-based prominence features for pronunciation and evaluation by Chiranjeevi Era Sir, Dr. Om D. Deshmukh, Prashanta Kumar Ghosh, which was published in from IIIT itself. So this particular paper, what it says is it detects the syllable stress for the L2 learners. L2 learners are not native learners, like the non-native learners are called as L2 learners. So which can be automated, and it can be and those results can be analyzed, and it can be given to the users so that they'll become good in their proficiency. So it depends on intensity level, duration, and pitch. That is nothing but prosody analysis. So why do we use syllable stress detection is to identify the syllables which are more emphasized in words or phrases, and which helps us in effective pronunciation and rhythm. So this pronunciation and rhythm plays an important role in everyday life. Without those things, are the thing which we want to convey might differ in very different ways. So automatic systems, though they analyze the acoustic features. So what this paper has worked on was working on acoustic features. Acoustic features are pitch, intensity, and duration between different syllables, like the stressed syllables. So if in a word the first syllable is stressed, and in the second word the last syllable is stressed, so that difference, the duration of time, that is analyzed, and the pitch, the intensity, all those things are analyzed. So why do we need syllable stress detection? As I've told, we need it for language learning, prosody and expressiveness, speech clarity, and intelligibility. So the work that I've done, let us first go through my data generation and gathering it. So starting off, I use the acoustic and context Fisher files. We have two major like predefined Libri and Fisher files which are used worldwide, where we can use them and do such type of any type of analysis. And so acoustic and context features are the same. Like the acoustic features are like pitch, intensity, duration, which we have discussed, and wave to wake features. What are wave to wake features is, in a speech we'll have waves, right? But the model cannot directly analyze those waves. So this wave to wake model, what it does, it converts the wave to a vector form. Vector is nothing but in a matrix form. So this acoustic and context, what they have worked on, it has 38 features. So the wave to wake features wave to wake has 768 features. Like my wave to wake model have generated 768 features for each and every syllable. Now, giving 768 features for each across some 769 rows for each and every syllable is very hard. Like the model will become overfitted, or it might not learn, or it becomes underfit. So what we did was, taking instead of giving 768 features, I did like feature chopping. So if there are some there are 768 row columns, not rows, columns for each and every syllable. Now I divided those 768 into some set of things, some set of columns which can be averaged. Like I averaged them, like I took the frame level frames, I took different frames from those 768, I averaged it and reduced it to some n, where n might lie between 0 to 20. 20 is max that I have taken, because the less number of rows we take, the less number of things we take, the better it might perform, because it already has 769 features. So computing 768 into 769 is harder than 20 into 769. So the model is performing better. That's what the process that I have followed. Now models. I've used three models, like three techniques. DNN is deep neural networks. VA is variational autoencoders, and contrastive learning. Where contrastive learning is semi-supervised, I can say that, or it is more towards supervised. We are planning to make them create a model which can do unsupervised learning also. So let us first go through DNN. So DNN is something but it has multiple layers. It includes input layer, hidden layer, and output layer, as we all know. So it is used for image classification and natural language processing. Now this thing is speech processing. So I used DNN, and it really performed well. Where I've used like 4 to 5 layers with 512 as starting, and then with two outputs. Like if it is stressed, it is 1. If it is not stressed, I took a label as 0. VA, variational autoencoders. So what DNN does, it doesn't scale any feature, like it doesn't reduce the dimension or anything. Now what this VA does is, it takes the input, sends it through an encoder. It reduces the dimensions of features based on some internal data which we provide, some like the learning of encoder. Once it has reduced the features, the latent space is generated. Latent space here is nothing but the important features that are affecting for one particular output. Now that is sent through a decoder. What the latent space vectors, whatever are there features, those are sent through the decoder, and the output is again given. So we started with n number of inputs, we will be getting n number of outputs, but inside we'll be finding out the main features which are affecting our data. So yeah, that's it is used for unsupervised learning. So as I told, we are working to generate unsupervised model. Now, what is contrastive learning? Contrastive learning is self-supervised learning. Self-supervised in the sense it learns by itself. So uh, basing on some unlabeled data. Now, whatever encoder we used here, so we can say that it is an extension of VA, but not exactly that. Now from the data which we get from the encoder, we are using an encoder here, but we won't use a decoder here. So we'll extract the features and we'll give it to contrastive learning. What contrastive learning does is, if there are 10 data points, it maps all the similar data points at one place, and the data points which are dissimilar from each other, it separates them. So the more common the features are, they are more grouped, and the dissimilar the features are, they are ungrouped. So here, what positive pairs means, the pairs which have more similarity. So it maximizes the similarity for positive pairs and minimizes the similarity for negative pairs. Where negative pairs is the ones which have which are more dissimilar. So once we are able to distinguish similar and dissimilar pairs, we are able to identify that which particular syllables are more stressed and less stressed, and how are the patterns coming, like the similarity and dissimilarity between the patterns. So that is why I've used these three techniques as of now. Now let us, when we come to the results. So on German data set, I got 92.363 as accuracy for DNN. It has increased to 93.46 as for VAE, and I can say that contrastive has given the best as with the 94.11% accuracy on testing data. Definitely on testing data, we have created different testing data for both of them. Like we didn't divide the whole data into 80/20. We have a separate new data set for the testing purpose. Now the ITA, like Italian got 92.95 in DNN, 93.25 in VA, and contrastive learning it has 94.2. And in all of this I use the same modal architecture. There were few cases where if I change the modal architecture, this Italian might go to 95, or German might go to 95 or something like that. But on a similar architecture, I just checked how much it performed. So my maximum accuracy that I got in different models were 95.83 in German and 95.5 in Italian. So I have developed different models using German and Italian data sets, which can predict the syllable stress of those using their web features. Thank you, and that's it.